So let me formally introduce Dr. Ma for his work. So Dr. Ma right now is in a postdoc in Professor Alberto Rodriguez's group in MIT. He has been focusing on a lot of different problems on tactile sensing as well as for robotic manipulation. In next year, in the coming year, he will join Shanghai Jiaotong University Naval Architectural, Ocean, and Civil Engineering in the Department of Mechanics as an associate professor. Without all further ado, I think I will leave the floor to Dr. Ma's work on the on high-resolution tactile sensing and perception for robotic manipulation. And I think from my perspective, this is a very great technology, not only for the robotic group, but also maybe for underwater vehicles, for fish swimming, as they may developing new pressure sensor, like a new type of pressure sensor for us. So with that, without further ado, I will leave the floor to Dr. Ma.
Thank you, Dixia, for your generous introduction. Good morning, everyone. Today, my name is Dr. Ma. I'm postdoc working with Professor Alberto Rodriguez. So today, I'm going to present our recent work research findings on the high-resolution tactile sensing and perception for the context of robotic manipulation. So the aging population and shortage of laborers have raised high expectation for the next generation robotics. But for decades, the industrial robots have been doing the repeatable work on the left side, like here, in the factories like this, where the environment is highly structured and everything is of high precision. And the solution for this is mostly open loop. But we are expecting the robots to tackle challenges in new scenarios. For example, in the warehouse, where millions of different objects are stored randomly, and the robots we need robots to find them, locate them, pick them up, pack them, and deliver them. And also in the kitchen scenario, like the forks and dishes are piled up randomly. The robots will also need to clean them, sort them, and maybe also the food needs to be prepared by the robot. Or in the next generation factories where different parts needs to be carefully put up together. Or even in the outer space where the environment is harsh for human astronauts, but the in-orbit maintaining needs to be done, and they can be done by the robot. For now, these these tasks are very difficult to automate, mostly because of the tedious interaction involved in these tasks. And the reactive is critical for the robot to accomplish this task. But the question is, how can we make the robots reactive and close the control loop? To close the control loop, sensing and perception is the key. For example, in 2017, we participated in the Amazon Robotics Challenge, where our robotic system can pick up the new novel objects out of a bin and place them in the desired places. This solution is possible only because we have developed the enabling technology, which is combined by two parts. On the hardware part, it's the RGBD camera for the sensing, and on the software side, it's the AI algorithm. With this enabling technology, we can close the control loop, which is mostly visual perception. But on the other side, in the above mentioned scenarios where interactions are critical, the visual perception only is not enough, mostly because when the objects are close to each other, the cameras will suffer from occlusion, and most importantly, the cameras cannot reflect the interactions between these objects. Just like human workers in the factory will need the hand and eyes to cooperate to accomplish these tasks, the future robots will also need the sense of touch to become part of the solution. So today I'm going to focus on the tactile sensing and perception. On the first part, I will talk about tactile sensing, which includes our sensor design, tactile sensor design, and how we process the low-level tactile information with it. And on the second part, I will talk about how can we consume this tactile information and use them in the context of robotic manipulation. Let's start with the tactile sensing. So we developed a tactile sensor called Gel Slim. It's a vision-based tactile sensor based on the technology of GelSat. It's high resolution and image-based. The sensing element is a piece of gel, which is soft and can be deformed when in contact with an object. And the camera inside the sensor can record the image, and we can process the low-level tactile information from the image. From video, we can see that it can give us real-time, very high-resolution tactile feedbacks imprint. Most research on this type of sensor were about reconstructing the shape of the contact. But I believe that this type of sensor is so informative that it's of great value for robotic manipulation. And the question is, what exactly are these information that's important for the robotic manipulation? On the mechanics side, it's the interaction that make the deformation, that caused the deformation instead of the shape itself. And the interaction directly is what matters for the robotic manipulation. So my focus of the research is to reconstruct the interaction information between the object and the hand, which includes shape, but also more importantly focus on the slip and force reconstruction. This is an exploded view of our Gel Slim sensor design. The sensor will have LEDs of different color on different location of the sensor so that we can shed the light of different color on the gel. And this gel is painted with markers and pigments on the outside surface. So, and we have a camera inside the sensor to watch the deformation of the gel. The working principle of this sensor is called photometric stereo, so that when the object is in contact with the gel, the local curvature is changed by the deformation, and that local curvature change will cause the refraction change, and we will observe the color change in the camera in the image space. My colleague Maria has trained a neural network to project the image into the shape of the object, of the grasped object, which is also the normal displacement of that gel. This will also paint the markers on the gel surface so that with marker tracking, we can also get the tangential motion of tangential deformation of this gel. But we must be careful that if you look carefully at the deformation, even if you only cause a normal displacement, normal deformation on the gel, on the camera side, you will also observe some tangential motion of the markers, which is because the normal deformation is relative to the surface of the gel, but that normal direction is not collinear with the optical path from the camera to the location of the deformation. So even a normal deformation will cause some image change on the marker location. So we need to correct those projection errors to decouple the influence of tangential deformation and normal deformation. With that, combining the normal displacement we measured and combined with the tangential displacement, we got the 3D displacement field on the surface of the gel, which is also give us the 3D deformation field of that gel. So then with that deformation field, an interesting inverse problem comes up. That is, what force field is the reason for such a deformation? An answer to this problem will lead us to the solution of sensing the contact force distribution. The technology of finite element method is a very powerful tool to simulate deformation and force distribution under certain loading conditions. I borrowed the technology from IBiM to solve my inverse problem. So the approach we propose is using the inverse IBiM to map deformation field into the force field that creates such a deformation. So the solution is to first mesh the gel into small element. And then each element here we use is 8 nodes hexagon element. And then the deformation of field of this gel is represented by the displacement of all these node points. And the stiffness matrix K can linearly map the deformation field into the external contact force that is creating this deformation. So our solution for this contact force estimation is called inverse IBiM. So we start with a sensor design. Given the sensor design, you can know the geometry parameter and material parameters. Then we mesh the gel and generate the stiffness matrix K. We know that generating the stiffness matrix is very time consuming, but since this is only needs to be done for once and can be preload to the system, so it costs no time when we run a system, when we run the system in real time. On the other side is to update the deformation field U, which can be run in real time. So this framework can run in real time. In our hardware setting, we can run it at 15 Hertz. The robot, here is the result. The robot is grasping a ball with the sensor and tries to insert it. Then we can see that the dense force distribution in the middle here. This is our reconstructed force distribution. On the left side is for comparison, the force resultant, which we usually get from a force dog sensor. We can clearly see that the force distribution is much more informative and discriminative than the force resultant. I performed experiment validation for the sensor's accuracy in measuring the resultant force. I did this with controlled experiment using an accurate force dog sensor and producing controlled interactions. We can see that they matched very well. In collaboration with graduate students in our lab, Siyu and Dong, we also showed that it is possible to detect slip in the contact patch by analyzing the motions of a marker. And the key for this capability is that these markers, if there is no slip, they should follow the rigid body motion of the grasped object. So when we find that some point is not following the rigid body motion of that object, we know that that point is starting to slip. This is used to detect the early stage slip, and which is very important for the robotic manipulation also. So the second part of my research is to consume this tactile information in the context of robotic manipulation for the purpose of perception. As we have seen, the tactile measurements from this type of sensor are high dimensional, real time, and with multimodality. And it's pretty challenging to use this information in the context of robotic manipulation. Take insertion as an example. Suppose a human is trying to insert an object into the hole. And key to such capabilities is to localize where that contact is. Even though we have no sensor embedded between the object and the environment, we know that the human being, it's believed that human being is capable of inferring that information with the sense on the skin between the hand and the object. We want to explore and know how to process the tactile imprint and infer such signals and design control policies based on that. Also, high-dimensional hybrid information is a burden usually for the model-based method. It's a good news for the data-driven method. So my colleague Yuan started this exploration by training a tactile controller that can adjust the insertion position based on the tactile feedback. This is the data collection process. And this is a supervised learning. And after training the model, this model can work with the objects it have never seen. As you can see in the video, it started with some collision with the environment, but because we can observe the tactile feedback, it quickly adjusts the new insertion pose, and so that it can insert that object into the narrow space. However, what's more interesting is to know what's the rational reasoning behind the working of this neural network. Because most of the time, the neural network is like a black box for us. And I'm quite interested in answering such an inverse problem. We find that the key to such a capability is that we can track the motion of the object with the tactile sensor. This video demonstrates that this idea. So this is an object we are experimenting with, and we have attached a few markers on the object to track its pose with a motion tracking system called VACOM. It can give us very high accuracy pose of that object. On the top left, we can see the real-time pose tracking from that system. At the same time, we can see our tactile imprint, which is shown in this image. My research gave us the capability of tracking the rigid body motion of the object only with this tactile measurement. So we use the 3D deformation field along with the pose of the gripper to retrieve the pose change of that object. Here we can see the comparison of the motion tracking result with the between the gel slim and the VACOM. We can see that with our tactile sensor, we can track the motion of the object at an accuracy of the same level of the VACOM, which is a very high accuracy. And the concept of this inferring extrinsic contact is like this. With the motion tracking capability, we can track the rigid body motion of the grasped object, but that object motion is not random. It is subject to its external contact. So its rigid body motion is subject to the kinematic constraint that is caused by its external contact. So the inverse problem is to decode the constraint of the rigid body motion and solve the contact location as unknown variables. By solving this inverse problem, we can know where the contact is and even the contact type of it. So we formulate this extrinsic contact sensing problem into a kinematic constraint optimization problem. For example, as shown on the top, the object is in line contact with a table edge, and the object is rotating around that edge. With the tactile sensor on the second level, we will see motion of those markers in the contact patch. And with that motion of these markers, we can retrieve the rigid body motion of the object. And these object motions will subject to the kinematic constraint. By solving the optimization problem with the location of the line as unknowns, we can know where the contact is. We evaluated this framework with the experiment. For example, using test it with point contact. The object grasps this tool, and this tool with the tip and this tool's tip is in point contact with the environment. And when we will use the tactile measurement from the tactile sensor to locate where that contact is. This is an experiment video. It's grasping this object, and this object is in point contact with the environment. This is the signal we got from the tactile sensor, and on this side, we see the real-time estimation of where the contact is. The red point is the ground truth, while the blue point is our estimation. These purple points are the marker's location. So when the gripper is moving and the marker is also moving, we can do the real-time estimation of where the contact is. As we gather more and more data, we can see that the error is smaller and smaller. So we further evaluated with more objects. All of these objects, we don't know their CAD model or its geometry parameters, but still we can estimate their contact with the environment with pretty good accuracy. It shows that the framework works for any rigid body without knowing its precise geometry. This is a very compelling feature for robotic manipulation. You don't need to know the grasped object's shape. And this is the results for our estimation. Red points are the ground truth, while the blue points are our estimation. We also evaluated for line contact, but in simulation. Because doing real experiment with line contact is not easy for now, because a line contact is so easy to break when the robot or the gripper is moving in open loop. So instead, we tested in simulation, and here the green line is our estimation, and the red line is the ground truth. We can see that, well, this dashed line is the initialization for this optimization. So we can see that even though you start with quite large error, it can still converge to the ground truth with very good accuracy. This work also tells us convincingly that tactile sensing is not only about force, which is kind of a belief for long, but it tells us that motion is very important for tactile sensing. And the motion tracking not only provides us with the capability of estimating the contact, extrinsic contact, but also we will see a little bit later that it's of high value for the control design. So here's a summary for the talk today. So the first part is about the tactile sensing. We introduced the sensor design and how to process low-level tactile information with the tactile imprints from the sensor. And on the second part, we talk about the contact position, which includes the motion tracking and also the localization of extrinsic contact with the environment. So the next final question is what's next? And what we are doing now, the answer is tactile control. As we can see from this video clip, that with this type of sensor, we are able to get vivid real-time feedbacks from the grasp, which is the gate to smart reactive manipulation. And the motion tracking here we discussed above not only enables us to estimate the contact state of the grasped object, but more importantly, accompanied with the contact force estimation, it has paved the road to tactile controller design. Such a controller is highly expected, but still missing in the robotic manipulation. So currently, I'm working with my colleagues to build the control loop, to build the control framework that enables the robot to do the closed loop control using these tactile feedbacks. And this video shows a very preliminary result. Here we see that in the simulation, the gripper is grasping an unknown object and tries to make contact with the bottom edge and rotate about the edge of the table without initially knowing where the contact edge is. The controller is making sense of the tactile displacement over time and estimates the edge while maintaining sufficient load on it and then rotate around it. We want to see our research results applied to real applications. We are interested in the manipulation tasks where the careful interaction is involved. So particularly, we would like to see our research making such challenging autonomous assembly possible, and to highlight the value of tactile sensing in these scenarios. With that said, I want to thank my advisor and colleagues who have made my research findings possible. And thank you very much today for this talk. Thank you.
Okay, thanks very much, Starling. So let's first, since we have a small group, 14 people. So let's just open the floor to first, and we have a little bit more time. So let's first open the floor to the people who have questions. I actually have 3 questions for Darling. So, but let's first open the floor to for the general public. So.
Yeah, I might ask a question actually, if that's okay.
Go ahead.
Yeah, first, thanks a lot. It was super interesting, amazing work. I was wondering if, as a fluid mechanicist and experimentalist, I wanted to apply your method to measure pressures of fluids. I would probably have very small displacements, and I was wondering, is this a critical limitation of this method? So will my accuracy probably be very bad if I only allow small displacements? Or are there ways we can account for that and also have a very accurate estimation of very small displacements?
When you say a small displacement, what's the level of that?
Yeah.
Microns, 10 microns or 100 microns? Or
well, in the range of less than 2 millimeters or something.
For this sensor right now, in this design, so let's say the sensing accuracy and the sensing sensitivity is based on the stiffness of the gel, which you can tune with the recipe of the gel, with the making recipe. And with that said, the current setup, we can measure the displacement in normal direction at, let's say, the accuracy of less than 0.1 millimeter. And the sensing range of depth right now it's about 1 millimeter.
Cool, super interesting. And did you ever think about, probably with Dixia, you already had this idea. Did you ever think about this possible application of your method for pressure measurements in fluids?
We have talked about it a little bit with, yeah. And he has similar ideas about that.
Okay, thank you a lot again.
Yeah, I think Gabe raised a hand. Gabe, just ask a question. So.
I didn't want to start talking for the first time before raising my hand after all. Thanks for the talk. It was super neat. It reminds me, or maybe it seems like it could play nicely with some of the biomimetic sensors that I worked with a while ago. So kind of continuing on from that last question, if you think about putting little, cilia type things, hairs sticking out of this. So, and then instead of holding a pencil and having the pencil be the thing that gets moved around, you can have little hairs that are the things that are being moved around. And then you can start thinking about the displacement of those hairs either being related to pressure or velocity, depending on how you set them up. So that could be kind of neat stuff. My question more, I mean, you could talk to whether that seems like it would make any sense, but my question more was, what about if we needed something like an array of these? Does that make sense? Or is this kind of already an array? Because I'm seeing a lot of little force measurements in some of these videos. Are these individual sensing pieces, or are they, how does that work?
Let's
like
do that video.
Yeah. Yeah, like this one was good, exactly.
Yeah. So here, each point is a measurement point. We will give that of, as you say, it's an array of 3D forces.
Yeah.
And we do that, but the sensor has only one piece of gel.
Okay. That's neat. So it's kind of automatically an array.
Yes. That's why we call it a high resolution tactile sensor. It gives us very high spatial resolution update.
Cool. So things like that seems like it could be pretty neat then. If you put a bunch of little hairs in them, then they could start not just measuring velocities and pressures, but distributions of velocities and pressures automatically. So that's the sort of information that we often would like.
So just to follow up, I don't know whether Gabe have a follow-up question. Just I want to follow up with Gabe, a question and a comment. Is that so? One thing, darling, is so basically it's a camera that in your gel, behind the gel in the camera, you have like a lot of dots that you are using camera to measure the dots movement. That which the sensor basically is a one piece of gel, right? Is that like a correct description of your sensor?
Yes. Okay,
so and follow up Gabe's question. So I think Gabe may be referring to the lettering sensor or the Hubble seal whisker. So in group with Michael Trenfuller, which is my supervisor, and they do is one single whisker. But that a whisker itself, Hubble seal have a face of a lot of whiskers. So maybe that's instead of having one whisker on your surface, there may be a couple whiskers on one piece of your surface, and which all these whiskers moving around, and we can track each whisker's motion with one sensor to feel the entire flow field. Is that what you're thinking, Gabe?
Exactly.
Yeah, I think that's actually something I was discussing with Darling before. I think this is maybe very interesting, for Gabe, for a Dave, in a group, for us to explore. So.
Mm-hmm. Yes, that's really a good idea.
Yeah. So. Oh, hi, Professor Lee. So.
Okay, so thank you, Dr. Ma, for this very interesting presentation. So I was from robotic field, but now I'm not. I'm in biomechanics. I did a lot of robotic manipulation when I did my PhD work, but I just have some application question. This is really nice design of sensors. So one thing remind me is, so you measure you can quantify the pressure, or just give a indication about the level, or you can quantify with how many kPa or something like that, or not?
It's quantifying.
It's quantifying, give you kPa's or something like that, right?
It's not only pressure, it gives you not only the pressure, which is normal pressure, but also give you tangential
Right, sure. Basically the tensile, right? Okay, so one thing is, so this sensor you are make is a relatively like a small area. For human application, we need like a kind of larger area compared to those things. Is that feasible to make, for example, make a whole glove or even something put under a like a socket of a prosthesis? I'm just curious about that capacity. Can you make it bigger and different kind of shape, like wrap around the human body?
That's a very interesting question. So this type of sensor, it's kind of easier to make it larger, but it's more difficult to make it compact and make it very small.
Okay.
So this adjustment is our first iteration. It's quite large. On the later part of the presentation, you already see that the sensor got smaller. So making it larger is fun. And some people have already made it of this type of sensor into applications like surrounded to the arm. So they build an arm with this type of sensor with the gels all surrounds the arm, and they have cameras on 2 different locations watching the deformation of that. It's the work of a Japanese group.
Okay. Okay, thank you. That's a very good point. Yeah, thank you very much. Yeah.
Any more questions from the audience? Okay, if not, like allow me to ask 2 questions. So one question is, I see like Darling, right now you are all devices is more like rigid. So what about like the device? Sorry, the grab stuff. The stuff you grab is rigid. So what about stuff that is solid? Sorry, like soft.
That's a good point, and that's my planned projects for the next a few years. Let's say I'm very interested in using this type of sensor in the applications of medical environment. So what I'm interested in now is how to use this type of sensor to estimate, for example, when you press here, you know where is the bone, where's the like muscle, and what's the distribution of these materials of different stiffness. And this type of application, I think, is of high potential in the robotic surgical. So we know that medical robots are used more and more widely, and but currently most of them are using only the visual feedback. The doctors do the surgeries. So I want to have this type of sensor embedded on those medical robots so that when it's placed, when their little finger is placed inside the human body, when it's touching the organ or the tissues, it knows, for example, where is the pulse, where is the blood vessel, or where is the tumor located with this tactile measurement.
So that's something that I think you may follow up with, like Dr. Qingguo Li and Matt, like who I will like introduce you guys to. So and another question. And the reason why I asked this question is that in deep water, like when they try to using ROV to grab like samples, a lot of samples or a lot of like animal samples, they are more like flexible. They're more like a jello-ish thing. So that's one thing like maybe to think about. Another question, another question, separate question is, right now the deformation is the sensing, the pressure, the deformation is coming from your direct contact with a different object. So what if say in case the gel itself is actually deformed while contacting other like devices. So for example, like for a concrete example, like a fish, that if we design something like this as a fish skin, or if fish So fish will actually, first of all, they are actually like all undulating by itself. So the skin itself is actually like deforming by itself while contact with other things. Do you have think about a way that maybe you can separate these two and like for better control each other?
That's a very good point. I think we can. I think it's possible, and right in my head right now, I think it's solvable because when what's caused the deformation, internal deformation caused by the fish itself, it's the acceleration, it's the iteration, right? Its muscle is changing its configuration, and that is changing the, let's say, the boundary condition for the gel. And if you take that into account for the FEM simulation, you can still decouple the internal reason for the deformation and the external reason for the deformation.
Okay, thank you very much. So let me ask if there's any more question from the audience. Okay, if not, let's give virtual applause to Dr. Moss, and thank you very much for your presentation, and also thank you very much for your today, and I wish you a safe trip back home. And I will do the communication and the introduction, and Dr. Moss' videos talk will be later online once he revealed the content and on YouTube, and I wish you a new career at the Shanghai Jiao Tong University. So, and thanks very much for everybody to join, and have a good rest of the Wednesday, and see you guys again. Bye-bye.
Thank you. Bye-bye.